Richard James will continue the presentation of this factorization tutorial with Factorization tutorial part 2a. As is most often the case, the statement of the problem says factorize completely. We therefore need to factorize each expression until it cannot be factorized anymore. A problem such as the one that we have here may be factorized as a difference of two squares. However, if we take a closer look, we should realize that the terms in the expression have a common factor of 4. So there we have a difference of two squares, but the difference of two squares have a common factor of 4. On the other hand, some candidates may see that there is a common factor of 4, and after factorizing, neglect the fact that the resulting expression is a difference of two squares. Let us first factorize the expression as a difference of two squares, because that is what it is. So the expression that we have right there, let us put it on the next slide, is a difference of two squares. So one may want to factorize as a difference of two squares. However, we may find that others may opt to make use of the fact that we have common factors. Usually, as soon as a first step in factorization is completed, then the candidate is gone merely on his way to another problem. But the statement of the problem is usually that we should factorize completely. So after factorizing, if we see that we have common factors existing still, then we may factorize again. Usually when we take the common factor and we end up with a difference of two squares, we do not continue to factorize the difference of two squares. We just move on our merry way. But as it is said before, we need to continue if it is possible that we can go through further steps in factorization. So although it is a difference of two squares, this expression that we have, it is a difference of two squares with the two squares having a common factor. So the two squares have a common factor. Factorize by taking the square root of the two squares. That's how we factorize the difference of two squares. Take the square root of the two squares. The first square is 4x squared. Take the square root of 4x squared, we get 2x. The second square is 16. Take the square root of 16, we get 4. So right there we have two possibilities, a positive and a negative, and we have that being indicated by including them in the brackets. So insert a positive and a negative sign. So there we have it. And we have factorized the difference of two squares. If we examine the resulting expression, we will realize that each factor may be further factorized by a common factor of 2. Factorize each one by a factor of 2. So we have right here 2x minus 4. Common here we have 2. 2x plus 4. Common we have 2. So we take the common factor of 2 and say 2 into 2x is x, and 2 into negative 4 is negative 2. We then come here and we say a common factor of 2. 2 into 2x is x, and 2 into positive 4 is positive 2. Therefore, we have factorized the expression a little bit more. The factors of 2 may be placed together 2 times 2 is 4, and then we have x minus 2, x plus 2. So place those factors of 2 together. 2 times 2 is 4. Then we have the x minus 2 and we have the x plus 2. And take note that what we have right here is exactly what we have here, which is correct. Now we are taking a second approach to the problem. The most basic principle in factorization is to make use of a common factor where it exists. The most appropriate approach is to take the common factor of 4 first. So always take a highest common factor if we can. So take that common factor of 4, and we say what? 4 into 4x squared is x squared, and 4 into negative 16 is negative 4. And we have x squared minus 4 remaining. Some candidates, after taking the common factor, x squared minus 4, to be multiplied by 4, they are gone, because they have factorized already. But they have not factorized completely, which is the requirement of the statement of the problem. So we have right there, again, a difference of 2 squares that we may continue to factorize. Factorize the difference of 2 squares by taking square roots of the 2 squares. Square root of x squared, x. Square root of 4, 2. And we have a positive and a negative sign. Surely the answer is the same as the one that we got in the previous approach. However, when factorizing, always be aware of the most fundamental principles and apply them appropriately. So, surely the answer is the same as the one that we got in the previous approach, and of course the one that we have right here. All of them are equal and all of them are correct. However, when factorizing, always be aware of the most fundamental principles and apply them appropriately, which is, if a common factor exists, factorize by first taking the common factor. At a glance, some candidates may interpret this problem to be a difference of 2 squares, and some will say, how is that possible? But it is quite possible under examination pressure and all of the other factors to be considered. By the time they take a second look, they will realize that it is not a difference of 2 squares. One is that 3 is accompanying x squared, and 3 is not a square. This prevents, so the 3 is accompanying x squared, and this prevents the entire term from being a square. And secondly, there is nothing squarish about 21. That's a new word. There is nothing squarish about 21. Surely we may factorize the expression by taking a common factor of 3x. So let us take that common factor of 3x. And of course 3x into 3x squared is x, and 3x into negative 21x is negative 7. 3x squared divided by 3x, x. Negative 21x divided by 3x is negative 7. So x minus 7 is what we have right there. Especially under examination pressure, it is not difficult for students to be blinded by the appearance of a problem. In order that you do not get defeated by the first appearance of a factorization problem, go to first principle. For each expression that you are attempting to factorize, examine it for the presence of a common factor. If you do that, you will never be blinded by the appearance of a particular expression, especially to be deceived that it is a difference of two squares initially. Here is another difference of two squares that candidates should not generally have problem with. They surely should not, unless, as is rarely the case, they do not identify one as a square number. And we will probably take a look at the reason for students not identifying one as a square number. In factorizing the difference of two squares, we need to make use of the square root of the squares. They will be enclosed in brackets and be separated by a negative sign in one set of brackets and a positive sign in the other. The square root of 4a squared is 2a. The square root of 1 is 1. 2a and then 1 in both brackets. We separate them, 1 by a positive and then by a negative. The order of the signs does not matter. We may place the negative and the positive sign in any of the brackets that we choose. There we have it. In this case, the product of A and C is 6 times negative 2, which is equal to a negative 12. The product is negative. We know that the numbers will have different signs. And because B is positive, we know that the larger number is positive. So we know, because the sign of the product is negative, that the two numbers will have different signs. The sum is positive. Therefore, of the two numbers that have different signs, the larger one is positive. Let us consider the pairs of numbers that will give a product of 12. We know 12 ones, 6 twos, 4 threes. The middle coefficient is positive. Therefore, the larger number is positive. Do not forget that they have different signs, because when we multiply them, the result is negative. A term that is not accompanied by any coefficient as a coefficient of 1. Also, there's really no need to go through a long and lengthy or even technical process if the coefficients of the middle components may be identified immediately. So, although there is no 1 here, we are sure that the coefficient is 1, because when we do not see a term accompanied by any coefficient, the coefficient is 1 by default. So we are sure that the two numbers that give the answer are 4 and negative 3, and they will be the two component coefficients of the single middle term that we have right here. For the first pair, the HCF is 3x. Taking 3x out, 3x is our common factor, and as we take our common factor, we will divide each term by the highest common factor. 3x into 6x squared, 3 into 6 is 2, x into x squared is x, 2x. And what do we know right here? Cancels completely, and as we have said before, when we have a complete cancellation, it cancels to 1. Anything divided by itself is equal to 1. The second pair, the common factor is 2. And what do we do? Again, divide each term by the highest common factor of 2. So, reduce those fractions and see what we get. that will give us 3 into 6, 2, x into x squared x. Do not forget that we need to have the common factor recurring. 3x and 2x inside of the brackets. Anything divided by itself is 1, but do not forget that negative sign. Again, we have 2 into 4 is 2. Nothing to cancel the x, 2x. And do not forget that anything divided by itself is equal to 1, and do not forget that negative sign right there. Finally, the common factor is 2x minus 1. That's nice. As I've said before, we will assume a mental process that we will show on the screen, because we cannot do something in our mind for you to read unless we have a representation of it on the screen. And sometimes we will include that intermediate step, so we'll have a nice mix as we go throughout the tutorial. But it is for the candidates to understand that these are the only necessary steps that will ensure that you secure your full marks for this factorization problem. So we will divide the expression by a common factor of 2x minus 1, and what will happen? What is left is 3x, and over on this side what is left is 2 plus 2. So we will have 2x minus 1 and 3x plus 2. Those are our factors. Although we have them in different order here, we are still correct. Here we have another one. Difference of two squares. Difference of two squares. And what do we do with them? Factorize them by taking the square root of the squares. Square root of 9a squared, 3a. Of course, square root of 9 is 3. Square root of b squared. The square root and the square, we know that they are inverse operation and will have cancelling effect on each other. So square root of b squared is b. And we will throw those into our brackets. And we will separate them one occasion by a positive sign and other occasion by a negative sign in any order that we choose. And that's all there is to it. What do we have right there? Here we have an expression that has 4 terms. We therefore expect to factorize by grouping. However, the first pair has no common factor but 1. Let us proceed to use a factor of 1. So the first pair has no common factor but 1. But let us go straight ahead and use it and see what we get. With the common factor of 1, each term will return as it is. That's easy. And then we take a common factor of negative 2 right there. So the second pair has a common factor of negative 2. So a common factor of negative 2, what do we say? Negative 2 into negative 4 is positive 2, and then we have the xy, so 2xy. And negative 2 into positive 6 is negative 3, so 2xy minus 3. What a disaster! Although it is not necessarily true, there is a great chance that we have not solved the problem correctly. This is because there is no further common factor, as we would expect that it would be the case when we are factorizing by grouping. So we do not have any further common factor to further factorize. But this does not necessarily mean that the problem is solved erroneously. And also, using 1 as a common factor does not prevent us from being correct. However, we would expect that when we are factorizing by grouping, we will get in another step another common factor that we can finish factorizing the entire expression, instead of having one that factorizes up to a point and cannot be factorized further. So, factorization by grouping, we expect that we should be able to continue. We cannot continue in this case, therefore we expect that something is wrong, but not necessarily. What we could do though is take another approach to the problem in which the terms are rearranged and see what will be the result of that. Do not blame our experience so far with this problem on the fact that we took a common factor of 1. So it is not because we took a common factor of 1 why we got to a dead end. Surely we have done it before, so we have taken a common factor of 1 before and we did not encounter such difficulties. So surely we have done it before to great positive effect. We could rearrange the terms in a more favorable way and see what happens. In so doing, I usually make the least number of changes possible, which is to relocate only one of the terms. Well, since we are at a dead end and we imagine that we should be able to go further, let us take another route. And we will take that route by rearranging the expression. And we will do it in the easiest way, just to relocate only one term. So that positive 6 goes there, and that's all there is to it. Later on, we will show that a common factor of 1 does not necessarily prevent us from factorizing an expression correctly. In the meantime, we will go to the next slide and factorize our rearranged expression, which is the one that we have right here. So let us proceed to factorize the rearranged expression. The first two terms have a common factor of 3. 6 divided by 3 is equal to 2, and 3x divided by 3 is equal to x. On the other occasion, we say that 8, 4, a common factor of a negative 4, the negative sign begins the second pair, use the sign that begins the second pair. 4 is the largest number that can go into 8 and 4, and no doubt, we have the presence of y in both terms. So negative 4y is our common factor. Negative 8y divided by negative 4y is 2, and negative 4xy divided by negative 4y is a positive x. Negative divided by negative is equal to positive on both occasions, and we have the negative 8y divided by negative 4y, and that is a 2 right there, and then we have the positive x right there. We will finish our factorization by taking a common factor of 2 plus x. 2 plus x is our common factor, and what do we know? 3 minus 4y will go into the other pair of brackets, like that. We know that further factorization is possible when the contents of the two pairs of brackets are identical. So when we have 2 plus x in one, 2 plus x in the other, then they are identical. Further factorization is possible because we have a common factor. If not before these tutorials, we should be quite familiar with the difference of two squares by now. So if we were not familiar with them, or the expression of that form before these tutorials, we should be familiar with it by now. And what do? Find the square root of the squares and enclose them in brackets. Square root of 9 is 3. Square root of 25m squared is 5m. So put the 3 and the 5m in those brackets and separate them with a positive and negative sign depending on which we choose. And that's all there is to the factorization of the difference of two squares. For this trinomial, the product of A and C is 2. 2 multiplied by negative 15 is equal to negative 30. As usual, a negative product indicates that the two middle coefficients will have different signs. The value of B is negative, which tells us that the larger one is negative. Let us consider the possibilities. So the product is negative. The two numbers will have different sign. The sum, which is B, the coefficient of the middle term, is negative. Therefore, when we add them, the result is negative, telling us that of the two numbers that have different signs, the larger one is negative. Those are all of the possibilities. So if we are using 30 times 1, 10 times 3, 15 times 2, 6 times 5, the larger one has to be negative because we have a negative sign for the sum of two numbers that have different signs. When we add numbers that have different signs, we subtract the smaller from the larger and the answer will take the same sign as the larger. Therefore, if we are adding two numbers with different signs and the result is negative, then the larger one is negative. So there we have it. We know that a coefficient of 1 is not usually written, or we may say that if a term is not accompanied by a coefficient, then we know that the value of the coefficient is 1 by default. The negative sign preceding the terms without any number implies that the coefficient is negative 1. So we have no coefficient number here, so we are sure that the coefficient is 1. The sign is negative, so we are sure that the coefficient is actually negative 1. And the combination that gives the negative 1 is negative 6 plus 5, which is correct. This negative 6 and positive 5 will be the two component coefficients of the single middle term that we have right there when we resolve it. So now that we know the two components coefficients are negative 6 and a positive 5, we will proceed to factorize. And we will factorize by taking a common factor. So take the common factor of 2x. And we will divide each term by the common factor. 2x into 2x squared is x. 2x into 6x is negative 3. Well, negative 6, so negative 3. And on the other hand, the highest common factor is 5. 5 into 5 is 1. Those will cancel and give x. 5 into negative 15 is negative 3. There's nothing to it. We will further our factorization by taking a common factor of x minus 3. So we will take a step further and finish up our factorization by taking a common factor of x minus 3. And what do we know? After dividing each term by x minus 3, the terms that will occupy the next pair of brackets will be 2x plus 5. And no doubt, by the time we are finished with all of these factorization tutorials, we will see other cases in which we have chosen to include the intermediate steps. And of course, we will still see others in which we choose not to include the intermediate steps. Here is the one that we have mentioned not too long ago. Taking a common factor of 1 does not necessarily make a solution wrong. The only common factor of the first two terms is 1. So take it. The first two terms have a common factor of 1. And what do we know? If we take a common factor of 1, the two terms will return as they are, x plus y. The second pair has a common factor of negative a. As we can see, a is common, and we always choose to use the sign that begins the second pair. So we have negative ax. Negative ax divided by negative a is positive x. Negative divided by negative is positive. And we have negative ay divided by negative a is positive y. There we have it. The common factor of x plus y causes further factorization to be possible. So x plus y is our common factor, and after we divide each term by x plus y, the other factor will be 1 minus a. And now for our other expression. No doubt we can factorize this in one step. We should be able to. The expression may look a bit complicated. However, do not forget that irrespective of what an expression may look like, if it is possible to take a common factor for all of the terms, then that should be our first option. Surely the terms may have many common factors, but the HCF of the term is 4p squared q. And we will take a look at how we arrive at the highest common factor. And as the tutorials proceed, or as we progress or proceed through these tutorials, we will take a look at another method that we may use to arrive at the highest common factor. So let us get with it. The highest common factor on this occasion is 4p squared q. Right. And we have what? 12p cubed q, which is this term, divided by 4p squared q is equal to 3p. And also we have 8p squared q cubed divided by 4p squared q is equal to 2q squared. This should at least be very harsh on your eyes. That I have realized. But we will proceed, because when I imagine that something is a little bit sophisticated, I will do something about it. I do not usually go through the tutorial, see something that is glaring, and at the same time I do not do anything about it. That is not how I operate, so we will see in the near future what we will do. Although in factorization we always take the highest common factor of the terms, because there are quite a few different common factors that we may take on this occasion, we were careful to emphasize highest common factor. So we are emphasizing highest common factor on this occasion because although we take it for granted that we always take the highest common factor, this one is a bit flexible, having quite a few possible factors. So we are emphasizing the highest common factor. And do not imagine that we have thrown this problem behind us, because here we are taking a look under the microscope at some other useful things that are pertaining to the solution of the problem. Let us take a look at how we arrive at the highest common factor of the terms. So there we have the terms. How do we arrive at the highest common factor? Simply, there is no difficulty seeing that the highest common factor of 12 and 8 is 4. So that's the first part of it. Next part. we now need the highest common factor of p cubed and p squared. And we know what students usually do when we say common factor of p cubed and p squared. They find the two numbers that can go into 3 and 2 without leaving a remainder, which in this particular case is not correct, because what are we doing? Let us see as we progress what we really are doing or saying, or what is applicable when we are attempting to find the highest common factor of p cubed and p squared. We therefore need the highest expression, power and all, that can divide into p cubed and p squared. Remembering that when we divide numbers that have the same base, we subtract the indices, is half of the battle. So we do not say the two numbers that can go into 3 and 2 because they are indices. When we are thinking about division, we subtract the indices. And if we remember that, then that is half of the battle. What is the rest of it? We therefore need the largest number that may be subtracted from both 3 and 2. The largest number is 2. So we are subtracting the indices when we divide. So instead of saying that, like as we said before, what is the largest number that can go into 12 and 8? And that largest number is 4. When it comes to the indices, we cannot say what is the largest number that can go into 3 and 2. We have to say, because when we divide, we subtract the indices, we have to say what is the largest number that can be subtracted from 3, and that number can also be subtracted from 2. That largest number is 2. No problem seeing that 3 minus 2 is equal to 1. That is possible. Although 2 minus 2 is equal to 0, it is still possible to subtract 2 from 2. For the p's, the highest common factor is p squared because 2 is the largest number that can be subtracted from the indices. What about the q's? We now need the highest common factor of q and q cubed. We therefore need the largest expression, power and all, that can divide into q and q cubed. Consider also that when we divide, we subtract the indices, and do not forget, if a number is not accompanied by any index, the index is equal to 1 by default. So we have q to the power of 1 and we have q to the power of 3. What is the largest number that can be subtracted from 1 and 3? The largest number that may be subtracted from 1 and 3 is 1. The highest common factor of q and q cubed is therefore q to the power of 1, which is equal to q. We will now take a closer look at the factorization of the expression. We will take the highest common factor as usual, and we will divide each term by the highest common factor. Divide each term by the highest common factor. And what do we know? Highest common factor is there. Then we say 4 into 12 is 3. P cubed divided by p squared, as we have right there, is equal to p to the power of 1 by subtraction of the indices. However, any number raised to the power of 1 is equal to that same number. Therefore, p cubed p squared is equal to p. The q's cancel completely. divided by 4 is equal to 2. We are cancelling. 4 into 8 is 2. And p squared will cancel with p squared completely. So the p's cancel completely. And what do we have there? Q cubed divided by q is equal to q squared by subtraction of indices. If a number is not accompanied by any index, then the value of the index is 1 by default. So q cubed divided by q to the power of 1 is equal to q squared. So q cubed divided by q is equal to q cubed divided by q to the power of 1. By subtraction of indices, we have q cubed divided by q to the power of 1. 3 minus 1 is equal to 2. So q to the power of 2. On the next slide, we will take a look at what we really mean when we say that something cancels completely, and why it has the particular effect on the entire term. So we will take a look at what we mean when we say that something cancels completely, and the effect that that will have on the entire expression. Before taking a look at what we mean when we say that something cancels completely, let us expand the expressions a bit. So whereas we have 12p cubed q, we know that we mean 12 times p cubed times q, and so on. So spread it out a little bit, and we will no doubt do the same for the highest common factor. Demonstrating what we mean when we say that something cancels completely, and not only that, showing the effect that such a scenario will have on the entire expression. Well, this is nothing new. Take a common factor, divide by the highest common factor. That's all we are doing. What do we say now? First, 12 divided by 4 is equal to 3. No problem. What about p squared into p cubed? What do we do? P cubed divided by p squared is equal to p by subtraction of indices. P to the power of 1, when we subtract the indices, any number or expression, symbol, term or letter raised to the power of 1 is equal to that same thing. And what will happen there? Any number divided by itself is equal to 1. So we may say that the q's cancel completely. That's what we are saying, that the q's cancel completely. However, it is more appropriate to say that any number or expression divided by itself is equal to 1. Q divided by q is equal to 1. That is what we mean when we say that something cancels completely. And what do we mean when we say that the term vanishes into thin air? So we say 4 into 8 is 2, and we say p squared will cancel p squared completely. The p's cancel completely. As discussed before, any number or expression divided by itself is equal to 1. So p squared divided by p squared is equal to 1. We may also make use of the subtraction of indices when dividing. P squared divided by p squared is equal to p squared divided by p squared, p to the power of 2 minus 2, subtracting the indices, p to the power of 0, and that is equal to 1. Do not forget that any number raised to the power of 0 is equal to 1. So p to the power of 0 is equal to 1. Subtracting the indices, we get p to the power of 0. Any number, expression, letter or symbol raised to the power of 0 is equal to 1. And what do we have there? Subtracting the indices again, we have q to the power of 2. Do not forget that since this one is not accompanied by any index, the value of the index that we assume is 1. whenever there is a complete cancellation by division or reduction of fraction, the result is 1, as we have demonstrated on the 2 occasions in different ways. It is also important to know that 1 is called the multiplicative identity because any number or expression that we multiply by 1, the result is the same number or expression. That is why when there is a complete cancellation, the term just seems to vanish away like that. So we know that these cancel, the result is 1. But anything multiplied by 1 is that same thing. So 3p. And it appears as if the q vanishes, and that is why some students call it 0, but it is not 0. We have right here again the terms cancel, the result is 1. Any number or expression multiplied by 1 is that same thing. So when something cancels completely, it cancels to 1. The 1 is then used to multiply the other terms and also the coefficient in the expression, and anything multiplied by 1 is that same thing. So it seems to just disappear, as we have it right there. Erroneously, students say that a complete cancellation results in 0. Do not forget that any number or expression multiplied by 0 is equal to 0. So therefore, if when it cancels to 0, we will have 0 multiplied by this, and it will turn out to be 0. And 0 multiplied by this term will also be 0, and we will not have anything in the brackets. So do not forget that any number or expression multiplied by 0 is equal to 0. That being the case, the terms will all result in 0, which is surely not correct. So the entire thing is not equal to 0. Therefore, when we have a complete cancellation, it does not cancel to 0. We are sure that it cancels to, what does it cancel to? 1. And the 1 is used to multiply the other portion of the expression, which ends up being the same thing.